So, who wants to know how to size an IsaMill? I'd like to know that. So, I'd like to welcome you to this SAG 2023 workshop where I'd like to go through the practicalities of including an IsaMill into your flow sheet. My name is Ion Gurnett. I'm a senior metallurgist from Glencore Technology with a particular focus on the IsaMill, and it's my absolute pleasure to take you on this journey with me. Now, before we begin, it's always customary to use a safety show. My particular one that really resonates with me of late is this one I'd like to share with you, and it highlights the normalization of deviance. We had an incident in the lab a few months ago where an operator had their arm caught on a rotating agitator shaft. It was an interesting incident, mostly because of complacency that had developed over time, where we had retrofitted newer models with additional safety gear but never went back and looked at our existing equipment. What I really want to stress here is if you make a safety improvement, you should always go back and make sure that improvement is carried throughout the process. And here we recognize that we needed to change a bolt and put some screen protectors on top of the tanks. The more you operate something, the more it becomes normal, and this is why it's always good to stop, reflect, and have a check whether it's really safe to operate anything. Now, what is the agenda for today? Well, I'm going to take you a little bit through the IsaMill technology fundamentals, a little bit on the Testwork and Scaleup, predominantly what to look for, what to understand, and how that influences your inclusion into your flow sheet. I'm going to take you through how to size an IsaMill, a little bit about why ceramic media is important, what the SG does, the size, and at the end I'm going to go over a few of the recent projects we've been doing, as well as a few of the IsaMill developments of late. So, hope you enjoy the ride. Now, the fundamentals. So, the purpose of the IsaMill is to liberate. We know valuable minerals are locked in the ore. We want to separate them through froth flotation or other processes. So what we want to do is we want to find a way to break them up economically. And historically, everyone has always used and gone after the easier deposits, such as Broken Hill. Because, you know, the finer you go, the more power you need, and hence your OPEX and CAPEX increases. Therefore, deposits like McArthur River here, with about a 7 micron grind size, don't typically get exploited first. And what happens when you need to start exploiting those deposits, and that's pretty much the story on how the IsaMill came to be. So, fine grain mineralogy requires a finer grind size. In the 1980s, Xstrata, or Mount Isa mines at the time, recognized that they had to go to 7 micron grind size. So, how do you go about it? The first step, as you would, what do we have currently in the market? So they went out, had a look, and then started thinking, let's try to get there with tower mills and ball mills. But when they tried it, they found that when you use those technologies, the power consumption is significant, and the steel media had a negative influence on the flotation performance. Iron dissolves in solution, precipitates on the surface of the particles and iron hydroxide, inhibiting your flotation response. So these technologies were trialed, but unfortunately no success. So what do? You start looking outside of industry and look at similar industries where there may be an application. And that's what started the IsaMill journey. And after a bit of searching and looking, a technology was found. We worked with we developed and met a partner called Netch, who were specialized in the pharmaceutical, food, and paint industry. They used these very small mills with small, expensive media. And when it was tested at Mount Isa, what kind of resembled a milkshake maker and a drill, what we found was the ability to stir the media ground sufficiently. So, what next? You had to make it work in mining. So, what does that mean? Larger scale equipment, make it continuous, and you've got to make the media usage cost effective. And that's pretty much what caused the IsaMill to go on its developmental journey. So, what's the timeline of this process? In the late 1980s, the first large-scale mill was developed, the M3000, which was developed by Xstrata and Netsch. The terminology I use when I talk about these mills is M for mill. The number is the size and capacity in litres. So M3000, 3,000 litre mill. That mill was then tested and prototyped and piloted in Mount Isa, and it was found to be a great success. So much so that the first official IsaMill was installed at Mount Isa mines in the lead zinc circuit in 1994. What did this do? Well, this then enabled Mount Isa mines to advance the McArthur River mine because they now found a technology that can sufficiently liberate at 7 microns. And this was a great start into the process. In about 2001, Mount Isa mines decided to commercialize the IsaMill to the wider market. Now, as we did that, we started talking to more and more clients, and in about 2003 we started working in South Africa in the platinum industry. And through those conversations a very good point came up. I really like your technology, but I'm not going to put 30 of them in, make them bigger. So a whole lot of work was done, and we tried to scale up to the M10,000. So we went from about an 855 kilowatt mill to a 3 megawatt mill. A lot of that development then allowed higher throughput rates and coarser feeds. We then went through this exercise again in 2017 for the development of the M15,000, 2020 for the 20,000, and in 2022 for the 30,000 and 50,000. Coarse grinding is really pushing this concept, and this is the area where the mill is headed. So more of the flow sheet should be able to be occupied with stirred mills. Now, how does the mill actually look in the circuit? So up here on my left, I've got a diagram of a typical mill layout. Good ways to think about it are that the blue is like a mill-only supply. Everything you see is a plant supply. So this is what you'd expect in a standard IsaMill circuit. Fresh feed will enter your feed pump box. It will then go through your feed pump, through into the mill. The mill will discharge and go through this discharge pipework where a portion will be recycled and the rest to discharge. Your media hopper, which charges your media, will sit to the side with a hydraulic isocharger which will pump the media across the feed pump box and into the mill. The design of the mill has a self-internal classification system, so once media is added, the media is retained. We now have removable rails. The rails are associated for maintenance because all these are on hydraulics, and you can shut the mill down, use the hydraulic rails to open it up, and do your maintenance within 3-4 hours. So, looks good from the outside. Let's have a look what's happening inside. So, inside the mill, slurry is pumped between 50 to 150 kPa. Inside the mill is a fixed speed shaft with a series of discs on it. Those discs change per operation, but typically it's 7 to 8 discs. Those discs, since they're on a fixed speed shaft, will be rotating around 18 to 20 meters per second. As those discs rotate, what you find is it agitates a whole bed of ceramic media. Inside that mill, you're looking at around 75% of that volume being filled with ceramic media, and those discs agitate this environment. When you add slurry, what you're doing is you're applying centrifugal forces which will then pull your coarser material out and let your fine material move through the center. What this means is your coarser material will typically be retained while your fines will move through the mill. When we get to the end of the mill, you'll notice the gap between this disc and this rotor is actually smaller relative to the other discs, and this is done deliberately. The smaller gap creates a hydrodynamic force which will push slurry out to the edges, and then this rotor will act as a pump, pumping back towards the front of the mill. What that means is coarse material that moves out here cannot move through the mill and out. It gets retained while it's ground fine enough before it can leave through the center. That is how the mill works, and that's how it internally classifies. The mill itself can typically take a top F80 of about 850 microns with a top size of 3 millimeters, and that's lately driven by some of our coarse grinding work. But the most important thing with a stirred mill is the media you select will dictate the feed that you can put to the mill. That is key. Now, the internal design, like I said, can change. Typically, it's 7 to 8 discs, small discs, large discs, different spaces, and this is all done to help the site manage wear. You want a mill to deliver what you want, but you also want to reduce the number of times you shut the mill down, so that's why we develop different components to allow you to do so. Now, I talked about that rotor and that classification, and I can talk and show you pictures, but what does it actually look like? And so that's what my next slide is. To prove that point and really demonstrate the effectiveness of that rotor, we thought it'd be a good idea to let's put a glass shell on a mill. So this is an M20 mill, and this is glass beads because we didn't want to use ceramics on glass, it might break it. And we started the mill up. This is a photo when the mill was running, but when the mill is stopped, the beads sit along the bottom of the mill. As the mill starts up, this zone gets an intense mixing zone, and as it stabilizes at steady state, this rotor acts as a pump and keeps all the material away. That's why in this picture you can see clear fluid, glass beads. That's that self-classification mechanism that I've been really trying to address. Now, what's that look like when you do test work? So, that internal classification is going to preferentially grind coarse material. As you grind coarse material, you're going to produce a more uniform product. This mill will scale up 1-to-1 with a full-scale installation. Here, we've got some of the older data from a paper back in 2005, but what you can see is, in the initial test work, you can see that the MRM plant IsaMill and the Century Lab scale mill produce very similar P80s and similar P98s. When the Century plant put in their full-scale mill, that P98 ratio increased dramatically. What that does is it will theoretically hurt your leach recovery and your flotation response. In this example, we did a rough study showing you the effect between the two technologies, and the IsaMill achieved probably a 2 to 4% increase in recovery. But if I do that in a model and say, let's say I model about 125,000 ton per hour copper leach plant, you're looking at about a 6 to 11 million USD revenue difference from that 2 to 4% increase in recovery. So it's very valuable to look at that. And when you look at mills, always look at the full PSD. Do not focus on that P80. So that's how the mill works. But how do you do the test work, and does the test work scale up 1-to-1? Spoiler, it does. So any mill will scale up with each other. We do a lot of our our test work at labs around the world. We accredit labs to do the test work on our behalf. We don't control the test work. We do it on the M4, which is a lab scale mill, 4-liter mill, or you can pilot it on an M20 as we have down here. We use these to obtain a specific energy. A specific energy is not the same as bond work energy. It is measured through total power via the VFD. It is not inferred by torque measurements. This mill will run a signature plot, and what we do here is a batch pendulum style test. So we have 2 tanks, batch pendulum, we fill one, pump it through the mill, send it to the other. And you do that enough times until you get to your grind size and measure your specific energy. That will scale up 1 to 1 with any size mill if it's performed in the accredited lab. Now, if I say it scales up 1 to 1, what you are aware of is you need to be aware of your ore type, size, media size, and density. That will really, if they're the same, it will scale up 1 to 1. Now, to really reiterate that point, I've got a bit of a diagram here for you. Same arrangement, trying to explain how it works. So, green is in, red is out. So if this is my feed tank, my feed will then go in through a feed pump into the mill. The entire sample will be ground through the mill, out and recovered to the second tank. I will collect the sample, I will measure the P80. When it's at steady state, I know my total energy. Therefore, I know the energy to go from this size to this size. And I'll be able to calculate my specific energy. We measure it so the particle goes through once. There's no chance of it going through multiple times, so you get an accurate representation of that grinding energy and reduction. Now, I then want to do my second pass on the sig plot. I reverse everything. This becomes the feed tank, goes in, through the mill, and back out. It's my second pass. And you do this enough times until you get to the grind size you want. So, pretty simple. But there are some intricacies, and these are some of the practicalities that I really wanted to discuss as part of this workshop. First one, why can't I use the bond work index for sizings? That's important. Some people can use 5-6 kilos, you need 15. Why is that? I'll touch on that. What you actually use for your sample, what the influence is of media size and SG, why is viscosity important, and I know as simple as it sounds, am I using the right particle sizing method? So let's go through these. Everyone knows, and a lot of people will use the bond work index to generate determination of specific energy. This is quite common in comminution, but it's a little bit more awkward in stirred mills, specifically once you go sub 100 microns. And the reason for that is the exponent, the minus 0.5, varies sub 100 microns. Secondly, all these mills are also slightly different, so there is a bit of variability that we've seen with bond works going out there. And really, to reiterate that point, I've referenced one of the papers from CMP 2017. As you can see, the exponent changes depending on your material. Hence, if one of these comes up, I would use bond work as a sanity check, but I would speak to GT. We can provide a specific energy from our database that might be a more useful figure to use. Now, what if I only have 5 kilos? Maybe I can use this. That is not necessarily true. The purpose of using 15 kilos for your sample is as a rough rule. You want to have enough sample to fill that mill voidage volume inside the test 3 to 4 times over. When you do that, that drives up your sample mass. Now, we did a sig plot using 15 kilos of sample on a surveyed mill. On left here, I have a signature plot. Along the x-axis is your size. Along your y is a specific energy. It's a log-log plot. As you can see, the linear relationship in the dark blue was the signature plot. We surveyed the mill and then put that on that signature plot, get 1-to-1 scale up, like I was talking about. Now, I had an extra 5 kilos left over, and I know there are some tests out there that can use 5 kilos, so I thought, let's replicate this procedure. Let's give it a go. And I didn't think it would work, specifically because of that steady state comment. And we ran the test, followed the procedure, and it developed that light blue line. That light blue line is about 30 to 40% less energy for the same grind size. It's the same sample, right? Why is it different? Goes back to that steady state. Small scale tests that don't achieve steady state typically hold up coarse particles between the media, your results will always be biased finer. And then that, if you're taking that through to a FS level, can really have implications when you start looking at what your required mill size, motor size is needed. So all I really want to stress at, be wary of your sample mass when you do a stirred mill test. Now, cyclone feed versus cyclone underflow. I'm doing my mill sizing. I want to do my sizing on the mill feed. We at GT prefer cyclone feed to cyclone underflow when doing mill sizings. All our sizings are sized off fresh feed, not mill feed. I understand fresh feed and throughput rates will be more than your direct mill feed, and it'll be slightly coarser in your underflow. What we find is those two typically even out, and it will line up well. What you can't do well in a lab, and I apologize, and I'm happy to take this questions if anyone disagrees, is it's very hard to get a designed representative cyclone split in the laboratory or on a full-scale mill. The fact that you can size off your cyclone feed gives you versatility if you want to size in open circuit or closed circuit. And it actually is a benefit in that regard. Now, media size. This is one of my favorite graphs. This is a bit of a study that was done on a mine site. And what really drove this discussion was, what was my required media size? We have a matrix, which I'll show you in a bit. And when we did this sizing, we recommended 1.5 millimeter media. Now, as turnover happens on site, things change. Recommendations and procurement objectives change. And what can happen is the wrong medium might get procured. Now, this study here shows you what can happen between using 3.5 and 1.5 mil media. In this case, you're looking at 7.5 kilowatt hours per ton. What does that mean? If I have a 100 ton per hour mill, that's 750 kilowatts of energy I can waste if I don't pick my mill media size correctly. As ESG and carbon reduction becomes more and more, the importance of selecting your media correctly is fundamental to your test work. Now, viscosity. Why is viscosity important? Viscosity in a stirred mill directly relates to your ability to grind. If it becomes more viscous, imagine a solid mass moving round and round. That basically drops your grinding efficiency. What we know is that operating density, particle size, and specific ore characteristics all feed into keeping that viscosity manageable. So what do? As a rule of thumb, we design our mill to operate at 20% solids by volume, going as per the design condition. In practicalities, a magnetite operation, that's 50–55% solids by weight. Coal operation, that's closer to 30% solids by weight. But by keeping that at the 20% solids by volume, we notice the most efficiency. And it's attempted to be described through this graph here. X is percent solids by volume, Y is power. Up around that 20%, you get about 100% efficiency. Once you move past it, that efficiency drops, and so does your power draw. Hence that locking up that I was talking about. Sizing. Sizing is important. There is no right way or wrong way to do sizings, but you have to be aware of the implications of your method you select. Now, laser sizes are work off the equivalent sphere methods. What does that mean? It means it takes your volume that it measures and assumes it's a sphere. That doesn't take into account particle shape. I borrowed this from a Malvern paper, but as you can see, the same volume exists between these two particles. But if you ran this on a laser sizer, the 39 micron sphere would record 39. But on a screen, you're looking around less than 20 micron. Now, if I'm looking at direct energy reduction to a certain size, that means, is my mill more efficient, or is it just the sizing method I used? So whatever you do use, you must be consistent. That's the message here. And I just wanted to reflect that through other sizings we've done, where we've done screen sizings versus laser sizing. In these signature plots, you can see the red line being the screen, blue line being the signature plot. Same material, same energy demand, just a different method of analysis. This is a tertiary grinding application. This is a zinc con regrind. 32% improvement just based on what you used. Quite important. 20% based on what you used. Particle shape needs to be acknowledged, and it has to be understood, particularly when you're looking at sizes greater than about 30 to 40 micron. And I wanted to also touch on the signature plot and full scale installations. So I've talked about scale up, but I've only given you one example. It's not really helping, right? So here is a few different examples. We've got 6 signature plots and a pilot trial and 6 examples of scale up. Gold at Kumtor. Green dots the survey, blue is the signature plot. Platinum tails, green dot's the survey, blue dot was the pilot run. MacArthur River, zinc concentrate, blue dot, linear relationship, green dot was the survey. Ernest Henry, magnetite mill, same relationship. Mount Isa zinc, same relationship. Arium, magnetite, same relationship. Papers are here. If you'd like to see them, feel free to contact us, we'll give them to you. But what I really want to stress is you do the signature plot correctly, these will scale up 1-to-1. So I'm not going to go into bad-mouthing different techniques that are out there, but what I would like to stress is this is not common and this is published information. This was an Amira campaign between tower mill estimates and measured plant performance. What you find is your vendor estimates when the mills went in versus the applied typically are out between 60, well, up to 60% at times. And here on the commissioning data at Sunrise Dam, you can see for a specific particle size, your energy demand can be anywhere between 130 kilowatt hours per ton. That's not 1-to-1 scale up. So potentially you want to get it right in the Testworks level. So where can I do these tests? Now, there are signature plot labs all over the world. We have ALS, Perth in Australia and West Coast, HRL testing in Brisbane or Core, Global Met Tech in Perth, Sedimen in Peru, Base Met in Kamloops, SGS Lakefield in Ontario, PT Geoservices Indonesia, King's Beads in China, and Karem back in Quebec. We are trying to get more and more labs out there, and what we want to do is have your labs as your first point of contact. They work with us, we review it, we work with them, get the conditions right, but we want them to have the autonomy and run with it. So we're very much open in that regard. So, how do I size an IsaMill? Probably one of the reasons you're all here. So, sizing IsaMills. This is a very, very heavy slide. It's a lot of words. Sizing an IsaMill is actually quite simple. What we really need is a throughput, feed size, product size, that dictates your media selection, specific energy for your particle size, which comes from your signature plot, expected feed slurry density, and or specific gravity. That feeds into your percent solids by volume. With that, we can pretty much do a sizing. We do prefer additional information, but that's mostly because we're engineers, but at the end of the day, it is quite simple to run with. With this slide, just notice the comment in the bottom right, we don't apply scale-up factors. We take the information you provide and we run with it. We don't add these 15% to the values because we want to be as honest as we can. So I've got my mill. Now, how do I select my media? Here I've got a matrix for you. So up the top here, we've got the feed size. Up the left here, we've got the decreasing product size. So if I want to select a media, say I want to go from 65 micron to 17 micron. I go 65 down to about 3 and across 17 micron. So what that means is if I want to do this efficiently, I need a 3 millimeter graded charge. So now I've got my media selected. Now we go look at flow rates. The mill is limited on motor capacity and flow rates. So if you're okay on your power, you just have to look at your flow rate. And that's what I've got here for reference for you. A rough rule of thumb that you do need to be aware of as well is the mill, all the components are rubber. So to protect the components, we actually interlock the mill at 70 degrees slurry temperature. That equates to a much significant higher surface temperature on those rubber components, but it's there to protect the life of the mill. Like I said, you want to design the best mill for you, but you want to make it last as well. So let's do a scenario. I've got a signature plot here, which was done. Client did this. I've got my linear scale up, and now I want to size it. In this case, I'm going to go 35 tons per hour. Feed size of 120 microns down to 35 microns. From this graph here, to do that I need about 10.5 kilowatt hours per ton. It's a float concentrate, float con regrind, so that's about 25% solids by weight will be feed, so obviously it needs to be densified going through the mill. My ore specific gravity is 3.85, copper deposit. My process water is 30 degrees, that feeds into your heat balance. And your cyclone mass split overflows 20%. That reflects how much you're actually feeding the mill. Put that through the calculations, I spit out a mass balance here. Key things that I look for in particular is maintaining your making sure your density is right, around that 20% solids by volume in your mill feed. Looking at your discharge temperature, ensure your heat balance is okay. And ensuring everything balances. This is the output from a heat temperature perspective. It's okay, it can remain open circuit, and a mill was selected. And in this case, we selected 1 and 1000, 500 kilowatts. This is a standard output when we run our mass balance, and this is something we give for free. We also give OPEX numbers, but it gives you an idea of how these mills run. Picture here, this is Layla. These are 3 and 1000s together. So this is kind of what you would get, just one of those mills. Now, we can do these mass balances for you, but let's be honest, you don't want to talk to us all the time. So to try and make things easier, we've developed a calculator. It's on the website. It'll give you a very rough sizing, but for me, it's good for desktop class 5 concept level studies. In the future, there'll be Naviswork models, so you'll be able to size a mill and take a Naviswork model and then just drop it into your plant design. So this is coming. So I talked about open circuit design. What happens if I go closed circuit due to heat? How do you actually do that? And so I wanted to give you a bit of an example in the design process. You want to make sure your density is still efficient to the mill. You can't be too dilute, otherwise you lose your grinding efficiency. You can't be too high because of viscosity concerns. I need to manage heat as well. So what you do is your fresh feed will come in, go into your discharge pump box. That discharge pump box will go up to a cyclone overflow. That underflow will be at that 20% solids by volume and feed the mill. Your fresh concentrate will be 30 to 25% solids, will be diluted here, and it will go through the mill at the desired density and then go back to your feed discharge pump box. Now I need to manage heat, so what else am I going to do? I'm going to add water. That water will cool it down, dilute it, much more manageable, controls it through to your cyclone overflow. And that's how our closed circuit design works for heat management. Now, this is pretty much me going through it. Key things here different. We typically have about, say, 125 to about 200% recirculating load if we need to do so. And this is how we control it. If I didn't do this and I ran it in open circuit configuration, what I'm doing is taking my closed circuit operating point, close to that 100% efficiency, and say I'm just diluting it to manage the temperature. I'm basically operating the mill about 70% of that efficiency, meaning for the same load, I will not be able to draw the same amount of power, and that grind will be less effective. That is why we do it. And what happens if I go really, really large to really, really fine? What is the reduction ratio I can do with that media? This is a bit convoluted, this slide, I'll be very honest. But rough rules of thumb for you is a media type should have a reduction ratio of 8 or less. You can go up to 10, but you start looking at efficiency losses. That rule of a reduction ratio of 8 is what we typically operate with. And what I wanted to show you here is if you're taking outside those ranges, you could also do a series grind. So you put 2 mills together with different medias, and what that does, it makes it more efficient. Here in a single stage grind, I'm looking at 60 kilowatt hours per ton. Now I have these 2 mills and they're operating at that. Say I take all the feed into one with a larger media, discharge into a second mill, what would that look like? And that's what we've done here. We've got 4 to 5 to break up that course. That's 13.8 kilowatt hours per ton. Then we've used 2 millimeters to go down to 12. What that means is there's a 17% reduction in energy by being more efficient with your media. And that's the change in the curve here. Single stage, 2 stage. So, thoughts when you design circuits. Ceramic media. Ceramic media is key and one of the key factors in any stirred mill on the market these days. Unlike most grinding mills, which use steel balls, we use high quality ceramic media. It's a considerably lower wear rate. We budget 8 to 12 grams per kilowatt hour. Some ceramic media vendors will tell you it's down to about 2 to 4 grams per kilowatt hour. So it's a lot lower wearing. And you don't have the issue of that iron dissolution creating those hydroxides on the particles. So it's much more efficient in that way. The grinding media you use, or the ceramic media, basically will impart energy on a whole stress intensity calculation basis. The stress intensity is basically the effectiveness in that grind. And what we've found is it correlates to 3 key areas: media diameter, media velocity, and SG. What we find is the diameter has much more of an influence in the velocity than the SG. So if you're trying to leverage aspects of break up material, larger media is going to be more effective than more dense media if it becomes harder. The rough rule of thumb is media must provide enough energy to break the coarsest particles at the rate at which they enter the mill. If you don't do that, you will get coarse particle buildup, which is why it's recommended that if you have an IsaMill, you need to contact us before you do a rash media change. Taking this to the next level, I've got basically try to visually represent that stress intensity relationship. The area shows you the size of the influence, and here you can see media size has a much bigger influence than SG, which is what we expected. So you're pushing this ceramic media, but how does it compare to a standard ball mill? And it's quite significant. I can talk about it, but data is data. Here we used mild steel versus various chrome medias and ceramic. If you look at your kinetic curve, you can hit your recovery 80 to 85% versus your mild steel, which is limited to about 20 to 40%, all from using ceramic media. Improvement in particle size actually liberates more surface area, and you can improve your fines recoveries as well, which you'd expect with a stirred mill. Taking that through to a full scale size, we've used Mount Isa copper ore. You can see the stepwise improvement from using that ceramic versus mild steel. And then you can see the charcoal pyrite recovery improved on that elephant curve via grinding finder. The elephant curve is that standard blue, dark blue conventional circuit. So what is good quality media? Everyone's got their own opinions. I'm quite simple. Good quality grinding media basically has a low wear rate and maintains its shape. It has to remain spherical, top left here. You don't want this angular compressed cubes. What this means is media is grinding on media, there's no fluidization, or flat, which means they've cracked in half and started to wear. If you see this sort of stuff, please talk to a ceramic media supplier. They will be able to help you. Now, ceramic media. We use 3.7, 3.8. Some of our competitors use higher SG medias due to the ability for higher SG media to be retained in vertical mills. Now, we didn't know this, but the higher SG media you go, the more expensive it gets. So we modeled a scenario. We know the wear rates between 4.5 and 3.7 are the same. So we modeled a stirred mill operating 2,500 kilowatt hours using about 12 grams per kilowatt hour wear rate. A little high, which I'll admit, but still within expectations. And what you see here is your difference in OPEX just on media. That there, to put it in a rough rule of thumb, you could buy a new M10,000 IsaMill every 3 years just in OPEX savings alone from your media selection. It is a big, big selling point, and it's a big influence in your project economics. But I've got new high SG media. Obviously, I don't know what I'm talking about. It's got to be more efficient. We've tested it. It's not in an IsaMill. I don't dispute other technologies, but in an IsaMill, it doesn't really work that well. We took a 3.7 SG media, SG media, ran a SIG plot, took 4.5, same material, same conditions, ran it again. You can see a step change for the same grind size. So from 20 microns, it goes from here about 40 to 50. And what causes that? And we have theories, but fundamentally we think the higher SG media, the energy you spend trying to move it doesn't necessarily make up that collision efficiency in the grind. So for an IsaMill, higher SG media isn't necessarily the most effective. I would encourage you to stay at that 3.7, 3.8. And to help optimize, we'll send this slide deck out to you, but this is a handy reference to have. So, recent projects. Got a few little more things to discuss what's coming up, what we've worked on, but I think this might be good. 2019, 2020, we commissioned this Minster B2 project in Juliaca, Peru. We supplied the M10,000 as a plant supply. Interestingly enough, this was more about that sharpness in the CSI distribution, so your P98, P80 ratio. Our duty here was 107 micron to 74 micron. The benefit here was to avoid potential overgrinding. It was part of a gravity separation tails regrind circuit in a tin operation, and it was done at altitude with the ISA control system. I know very well about the altitude part because I went and commissioned it and got altitude sickness while I was there. Hell Gold. Hell Gold is a gold mine in South Carolina in the US. We supplied the M10,000 as part of the IsaMill supply. It's a pre-leach grind duty for a gold operation. Pre-leach grind is one of the main duties you see with the IsaMill. It's why it feeds into our Albion process. But here we were going from 43 micron to 13, closed circuit configuration. The IsaMill was originally chosen to replace 6 Metso SMDs. The SMDs were unable to achieve the required P80, and like I said on that scale up you saw with the MacArthur River example, produced a wide size distribution, high CSI ratio. And the maintenance side of it wasn't great. So that was the original intent. We went in, we commissioned it, it's running well. In the US, recently commissioned Corbin, processing coal to tails. These mills are 3 mills in series, grinding from 40 micron to 5. This was the first remote commissioning we did during COVID, but was quite successful. Red Dog, this was the first M15000 mill only supplied. This is the first mill we've done in a quaternary grinding duty, situated in the Arctic. We're going from designs 150 micron to 60. At times it's quaternary grinding, it fluctuates. But this was the first M15000 commissioned. This is the first one we've done as a concrete plinth versus steel structure. First it was connected via coupling with a synchronous motor. So this mill has the ability to operate at pretty much any speed. ATK. This one was recently done about 6 months ago. An M10000 was supplied as the grind simplified plant supply. This is another pre-leach grind duty, really reflects that CSI ratio I've been talking about, going from about 25 micron to about 4. Here's the mill installed. Here's the guys that did it. Good duty, went pretty well. Abra, M500, little baby mill. This is processing lead concentrate, going from 100 microns to 40. Some of the things here that's really worth mentioning is the rapid rate to bring these online. This mill was commissioned on water within 3 days and was the first small scale mill to include automated charging and modulating recirculating valves. That's pretty much a standard on our larger mills. Our smaller ones, not the same. West Musgrave, 3 mills are supplied for that, 165 to 25 micron, just a model in the plant. And lastly, I just wanted to say, if you go to our website, you can see our installation list. As you can see in the last few years, it's very much kicked off and we've been very, very busy. So, developments. Talk to you about what to look for in test work, what you size. Talk to you about some of our recent projects, but where are we headed? We're in a culture of continuous improvement. You can't just keep things steady. So what have we done? And that's what I'd like to go through. We have changed the design. This bottom here was the original plant design. It was large, big footprint, really nice to operate, but some of the feedback we got wasn't that it could be more efficient. And so we took it upon ourselves to really reduce the cost of the plant, make it more efficient, make it better for the end user. We sat down, got a lot of feedback, and we redesigned it from this into this, which you saw earlier on the presentation. The biggest fundamental change between these designs is where we stored the media. In the old design, the media was stored under the bin, in the bin under the mill. We're now producing 20,000, 30,000, 50,000. Imagine having to store all that media under a mill. You're really going to drive the height up. So what we've done is we've recognized that the rotor has the ability to pump media out of the mill. What does that mean? It means that you can lower your platform where your limitation is your gravity returns on your oil systems, and that allows you to save 23 to 30% of your capex steel and concrete costs. We've tied systems into plant supply, so you don't have dedicated gland water isocharger systems. We've been asked to make the rails removable, which we've done. And we've just tried to make it a lot more compact. What does that mean? It means it basically sits in the footprint of equal size competitor mills now. So it's a smaller footprint than what's out there on the market. Disc designs. So we recognize that discs will change. We have been working on disc designs throughout the life of the mill. We've worked on components, we've worked on rubber materials, and we have tested these with Netch and have a history of nearly 100 years. We have got different spacers, different discs, and what we're trying to do here is trying to make the mill more efficient to be able to draw that power while maintaining that wear relationship. What you'll see as this goes on is as we go coarser with our feeds, some of these discs you'll see become more industry standard. Acoustics. They're a really interesting area. We did a whole lot of test work back in like the early 2010s, and we developed a unit that could measure, interpolate acoustic frequencies on the length of the mill. And the purpose of this was to primarily look where your media is. Let's see if there's changes in frequencies which will correlate to wear and give you more acknowledgement of when wear events are happening. But some very, very, very smart people recognize if you put these in the right spot, you can actually infer a particle size. So we tried to develop an acoustic unit, which is what you see top here on the right. Realistically, that's a pretty expensive unit to try and employ around sites. So what we've done is we went, let's go back to first principles, let's make it cheaper. So we did basically what I call a budget acoustic analyzer, but it works. We've been testing that to try and reach down to 10 micron slurries. What we find is there's a bit of a monopoly on the market, sub 75 micron, and what we found is this unit is able to accurately measure that. It has to be in the right streams, but we're currently testing it in more detail and trying to push this down the development pathway. Expect something to come through this in the next few years, but it is a very exciting prospect. Segmented shell. I've talked to you about the 30,000, the 50,000. If you want to purchase a mill larger than a 20,000, you start getting into issues with how you make spare parts cost effective. It's very hard to ship a 50,000 litre rubber shell. So you have to segment. And so what we're trying to do is find ways of doing it and make it cost effective over the life of the parts and make it easier. This whole purpose here really drives this whole segmented shell liner concept. Sorry, my clicker seems to have stopped. Now, I've talked about the segmented shell liner. Let's start talking about coarse grinding. Coarse grinding is something I'm particularly involved in and something that you'll see grind more and more in the future. We initially did coarse grinding test work back in 2008. At the time, the largest media available was 6 millimeters, which coincidentally is this media here. More and more ceramic media suppliers are starting to develop larger media. They think coarse grinding and stirred mill is the future. So what we have here is the pathway here. So this is about 2 mil, 5 mil, 10 mil, 24 mil. It's getting bigger. So what is that going to do? I already told you your media size will influence your grinding efficiency on coarse. So what will happen next? And that's what I'm going to try and give you a bit of a sneak peek in. We know that the IsaMill was developed for a sub 10 micron grind size initially, and it does that very, very well and has been very, very successful in that duty. It can do coarse. To kind of demonstrate this, I've got 2 CPF feeds, coarse particle flotation, whether it's through a JMO or another one on the market. And what I want to show you is you can take it, get good linear relationships, and you can do your series grind or a single grind, but the IsaMill can break up that material and do it efficiently with 1-to-1 scale up. We did a trial in Manitoba. We're publishing a paper at CIM in 2024 on the results of this trial, but we ran these coarser medias through an M100 here in the plant. And what we found was with 8 millimeter media, we're able to produce a sharper product size distribution to the existing ball mill. So about the same power, much sharper, much more efficient on the fines. And with the 10 mil media, we're able to replicate the performance at about 80% of the efficiency. So as we move to power savings, energy efficiency, stirred milling is going to go up there. And this is just reiterating what I said. And some of the highlights you can take out of it. The IsaMill does work in coarse grinding applications. I'm comfortable up to a mil. I'm trying to take it to 2-3 mil feed now. Higher SG media does not work. I haven't got the picture up here, but that weight to move the media never made up for the grind, and we kept bogging the mill, so that didn't work for us. The 10 mil was very energy efficient, and the sharpness exists. So that is the future. And I know everyone talks about this, but we looked at the IsaMill HPGR combination back in 2008. This is a 2011 paper on it. That is the future, I feel. And if you can get that 3-4 mil, I foresee ag IsaMill combinations where you have a future with no steel media. So you have a lot better control of the circuit. Anyway, like I said, my name is Ion Gurnett. I'm happy to have presented this to you. If you want to contact us, I've got some QR codes here for you. That should allow you to get through to us. If you have any questions, please reach out. Always happy to help. Thank you.